In electronics, materials are classified as conductors, insulators. And semiconductors and their conductivity depends on their atomic structure. Conductors are made of metallic elements such as copper. A copper atom has a single outermost electron that can easily escape the nucleus and become a free electron. Under an external electric field, these free electrons move directionally, forming an electric current. What about insulators? They are made of non-metallic elements or polymer materials. Their outer electron shells are close to a stable 8-electron structure, making them difficult to conduct electricity. So what is a semiconductor? The outer electrons of semiconductor elements lie between those of metals and non-metals. As a result, their conductivity lies between that of conductors and insulators. For example, silicon atoms have 4 outermost electrons. Each silicon atom forms covalent bonds with 4 neighboring silicon atoms. Electrons in covalent bonds are not as active as those in conductors, nor are they as tightly bound as in insulators. This gives semiconductors their intermediate conductivity. If semiconductors are not the best conductors, why use semiconductors instead of conductors? This is because pure semiconductor crystals have excellent material uniformity. By adding different impurity elements, their conductivity can be modified. This controllability enables the creation of electronic devices with different functions. The most common semiconductor materials are silicon and germanium. There are also compound semiconductors made of 2 elements such as boron nitride and silicon carbide. Let's take silicon as an example and look at its crystal lattice model. A silicon atom has 4 outermost electrons. It forms covalent bonds with 4 neighboring silicon atoms. This creates a 3-dimensional tetrahedral lattice structure. This spatial structure is not easy to visualize. So when analyzing semiconductor conductivity, a simplified planar lattice model is often used. The particles that carry current in a material are called charge carriers. In conductors, free electrons are the most common carriers. So what carriers exist in semiconductors? In silicon's lattice, electrons exist in covalent bonds. Due to thermal motion, some electrons gain energy. They break free from the covalent bonds and become free electrons. At the same time, a hole is left behind. When an external electric field is applied, free electrons move directionally, forming an electron current. Meanwhile, electrons continuously fill nearby holes, creating an effective hole movement known as hole current. As we can see, semiconductors have 2 types of carriers. They are free electrons and holes. Together, they determine the conductivity of the semiconductor. Based on these principles, there are 2 main ways to change semiconductor conductivity. The first is to change the concentration of free electrons. The second is to change the concentration of holes. So how is this done? By doping pure silicon with a pentavalent element such as phosphorus. Phosphorus atoms replace some silicon atoms. Phosphorus atoms have 5 valence electrons. After bonding, 1 extra electron becomes free. The more phosphorus added, the higher the free electron concentration. Free electrons become the majority carriers. This type of material is called an N-type semiconductor. Similarly, doping pure silicon with a trivalent element like boron. Boron atoms have only 3 valence electrons. When forming the lattice, 1 electron is missing, creating a hole. The more boron added, the higher the hole concentration. Holes become the majority carriers. This type of material is called a P-type semiconductor.